All right, here we go. View, let's turn off the dual page. Off. Full screen. Okay, so here we go. So universal gravitation. Am I safe in assuming you guys learned a little bit about this last year?
Yeah.
So you guys all know that any two objects that have mass. Hang tight for 1 second. Let me just take a quick look. No. Oh, I'm looking at the wrong one. No, I'm looking at the right one.
Pretty well.
This, at the very least, looks better. Yes. Great. Cool. Thanks, Ransom. Have a good one, buddy. All right. Okay. So. Okay. So here's the deal, guys. So usually, when you think of gravity, you think of gravity being the thing that makes the ducks fall in my classroom, right? Gravity is what pulls stuff towards the earth, right? Okay? So gravity holds us and objects to the earth. You guys know that, right? Okay? But technically speaking, there's nothing special about the earth. It's not like things are like, ooh, earth, I'm going to go to that. Okay? Any two objects that have mass, are gravitationally attracted toward each other. Very similar to the fact that any two things with magnetism are either attracted or repelled, depending on the poles, but, they attract each other, right? Okay? And I think you guys know this, the sun holds the Earth in orbit, right, with gravity. Gravity is why the Earth doesn't float away from the sun. It's why the moon doesn't float away from the Earth. It's why the sun doesn't float out of our galaxy, okay? So it attracts objects of mass, okay?
What holds the sun in place? Or what holds the sun?
The masses of the... Yes, thank you. Sorry, this is where I run into a little trouble because some of my astronomy knowledge is a little sketchy. What do you got?
What's the center of the Milky Way?
It's a gigantic black hole.
Yes. And so there's a tremendous amount of mass, provides gravity.
Well, so far I haven't ever get in.
Wow, you guys are all... Okay, so are we all good with that? Do you guys understand this idea that any two objects that have mass attract each other? Yes?
Yeah.
All right. So Newton is the dude who discovered that. As the story goes, he's hanging out one day looking at the moon, thinking about why doesn't the moon float away, right? Like he knows that objects, if there's no force on them, they go in a straight line, right? So he's picturing the moon going around and around and around. And he's like, why doesn't the moon float away? When, as the story goes, an apple fell out of the tree and hit him on the head. And he said, gravity, right? So is that true? I don't know, but that's the story. So he was able to come up with this equation, Newton's law of gravitation. Okay. It is called a law, but I understand why you would say that, because it falls apart in some, yes, in some frames of reference. Okay, so anyway, what he discovered was that the force of gravitational attraction between two objects can be calculated by multiplying this universal gravitation constant. All right, and this is a constant. In the same way that pi is a constant, if you take any circle anywhere in the universe and divide the circumference by the diameter, you always get this magic number pi, right? And I keep wanting to say Einstein. Newton discovered similarly that there's this universal constant that relates the force of gravity to the masses of the two objects, and r is the distance between the centers of the objects. So, yeah, center of mass. Center of mass. Sorry. I always oversimplify this for my regular class. Is that going to be true? Yes, that is true. Hold that thought for a minute, because we gotta talk about the shell theorem, I think, before I give that the answer that it deserves. So hold that thought for a minute, because it's not entirely true. All right. So I guess to be specific, technically speaking, this equation gives you the force of gravitational attraction between two particles. Okay? And once your particles have size, then things get a little bit dodgy, and we're headed down that path in a minute. Okay? Exactly, yeah, right, because a smaller radius would mean more force, right? Okay, so is everybody good with that? Okay, sorry.
I just said sounds like some calculus.
Yeah.
Oh, no.
Okay. So important things to notice. First of all, so you've got these two objects. I'll draw them as little balls. So here's mass 1, here's mass 2, right? Okay? So it's a mutual force. All right? So when you calculate this force, you're calculating the force with which mass 1 attracts mass 2, and by Newton's third law, that's also the force with which mass 2 attracts force 1, right? So those forces are equal, right? Does that mean they're going to move the same amount? No, why not? Because it's going to depend on their masses, right? So you can certainly find the accelerations of the two objects by just dividing by the masses of each of the objects, right? Follow? All right, so this equation is talking about, so this allows you to calculate the magnitude of the gravitational force of attraction. This equation is the equation that you use to calculate the vector. And so you'll notice it's the same equation, and then this times r hat just means in the direction of the radius. Okay? So in other words, here's the radius. Notice the forces point along that radius. Follow? Okay, so that's all that means. Please don't think this, so you're not actually, you're making r into a unit vector in the direction of r. That's what the little hat means. Follow? Okay. All right, so in the course of going through the problems in the book, I don't think I've ever used this. I always use this, and then I just understand that the force, is in the direction between the two objects. Cool? All right. Any problems with all of this? Too quick? This is all stuff you guys have seen before, yes? Okay, cool. All right. If you've got a collection of objects, so suppose I've got M1, M2, oops, and M3, okay? And I want to find the force of gravitational attraction on mass 3. Well, it's literally just vector addition. The idea is mass 1 is going to attract it this way. So here's the force of gravitational attraction from mass 1. Here's the force of gravitational attraction from mass 2. So to find the overall force of gravitational attraction, you just use vector addition and add the two vectors. Does that make sense? All right. The book gives that a fancy name and calls it the principle of superposition.
Oh.
You're finding that force. I don't even know why it has its own special section in the book. It's literally you're just adding forces, right? Follow? Okay, cool. So a minute ago, Alex said this sounds like some calculus. So if you want to find the force of attraction, I don't remember where, if it's in the notes or if it's in the homework or what, but at some point we'll do this problem. Suppose you had a rod and a little particle mass and you wanted to find the force of attraction between these two objects. That's going to require some calculus, and I don't know if it shows up in these notes or what, but at some point in the next day or two we will do that calculation. I'll show you how it works. And honestly, I think for the purpose of the AP test, that's about as complicated as they get. It's like a particle and a rod. You know what I mean? I don't think they get into any crazier, any other crazy shapes or anything. Okay. Okay. So I will make sure that we do an example of that in the next day or two. Well, it won't be tomorrow, obviously, but all right. So back to what Alex was asking about before. So if the object is a uniform sphere, you can treat the mass as being located at the center of mass. Okay. Even that statement is a little bit dodgy, so kind of put a little asterisk by that, and we'll talk about that more here in a second. Okay. I think the big thing to get out of this is that you can treat these forces as vectors and add them just like you'd add any other vector. Cool? All right. Okay, so here's an example where, we are going to basically just work through and figure out the net force, right? Okay, so here we've got mass 1 being attracted by mass 3 and mass 2, all right? And it's asking us to find the net force. So before I go through the calculations, I want to point something out to you. I remember the first time I did one of these problems going through, as I was going through it, my knee-jerk reaction was I thought, okay, well, mass 2 is here, or sorry, mass 3 is here, mass 2 is here, so my force of gravity is going to act that way. But that's not actually right. And some of you guys are shaking your heads already. What's wrong with what I just did? Yeah, kind of. Which of my two objects is mass 1 going to be attracted to with more force? Mass 2, right? Because it's closer, right? So it turns out that my force of attraction actually acts in a direction that's closer to mass 2 than it is to mass 3. Does that make sense? Okay. So when you do this, like I was saying, you're finding net force. Make sure that you focus on on one object at a time. You know what I mean? Like, do I want to find the net force on mass 1, the net force on mass 3, the net force on mass 2? Pick an object and focus on that one object. Okay. And obviously, the problem will state which one it wants you to look at. All right. So let's take a minute and kind of run through this. So if I wanted to find the force of attraction between M1 and M2, notice they're a distance of A apart. So this F1, F2 here, let's figure out what that would be. F1, 2, that's the force of object 2 attracting object 1. Well, that would be G times M1 times M2 all over A squared, right? So that's this blue vector here. Good. All right, and similarly, I could find the force of attraction over here. That would be, sorry, I want to do it in a different color. So the force of on object 1 from object 3 would be G times M1 times M3 over 2A squared, right? Which is really 4A squared, right? Got it? Okay. So that's that. And so then, as I was saying before, you can just do your vector addition, right? Here's this force. Here's this force. You could certainly find the hypotenuse by using, Pythagorean theorem. You could find the angle. Cool. Any problems with that? Okay. Cool. Do I need to say anything else about that? I think it's all pretty straightforward. Okay. Cool. All right. So here we're just going to rate these in terms of the largest net force. Let me make sure I read this. Let's see. Rank the arrangement according to the magnitude of net gravitational force on the particle labeled M. Greatest first. So let's start with that. Which one of those is going to have the largest magnitude of net force? Okay, what do you guys think? 1? 1 seems like it's probably the biggest to me. That's my knee-jerk reaction because all of them have, sort of one force a distance d away, right? The issue, though, is that, so this is going to be a big force from the close object and then a little force, but they're both in the same direction, right? Whereas these guys are working against each other, right? You're going to have a big force pulling it this way and a little force pulling it that way, so your net force is going to be smaller, right? And then I think 2 and 4 are equal, right? So the question is, what's bigger, 2 and 4 or 3? 2 and 4, right? Because they're not working against each other, right? So I think that the answer ought to be 1, 2 and 4 tie, and then 3 is the smallest, right? Agreed? All right, let's see. Don't look. Question B. In arrangement 2, is the direction of the net force closer to the line of length D or the length of capital D? So in this one, which way is my force going to go? Is it going to go more this way or more up-ish? Closer this way, right? Oh, that's, well, yeah. Yes, closer to D. Sorry, guys. All right, cool. All right. I remember, like I said, that you guys seem to be right on that, but for me that was not. I gotcha. Okay. All right. So we talked about this before when we had those two objects. I said, are they going to have the same acceleration? And you guys said no, because they might have different masses, right? So the idea is, if you want, you can calculate the acceleration of gravity on a planet just by taking, so here's the Earth, right? Oh, nope, that's not the Earth. Here's the Earth. Here's you. Hello. You're floating for some reason. You also have one really large arm. You actually look sort of like some sort of Japanese character. Right? Okay, so anyway, so gravity is pulling you down with this force, right? So if your mass is lowercase m, then your acceleration would be this force divided by lowercase m, and it's going to leave you with this, right? Well, there's your acceleration of gravity, right? Follow? Big M, oh, good question. Big M would be the mass of the planet or moon or whatever it is that you're on. And r is the distance you are away from its center. Cool? All right. So that gives you the magnitude of the gravitation acceleration if you're a given distance from the center of the Earth or planet or whatever. Notice what this tells us is the farther away you are from the center of the Earth, the less acceleration of gravity there is, right? Which makes sense because there's going to be less force, right? As the radius goes up, your force goes down. Okay? And so when we use 9.8, that's sort of like an average, you know? The acceleration of gravity is not exactly 9.8 at all places on Earth, you know? There are locations where that's true, but... so anyway, this little chart gives you some different values, you know, different altitudes, different accelerations of gravity. And I think the big thing to notice is that as your altitudes increase, your acceleration of gravity is decreased, right? Cool. Okay, cool. All right. So that was what I was just talking. This top bullet up here is what I was just talking about. The calculated acceleration of gravity is going to differ slightly depending on where you're at. Cool. All right. So when you calculate your gravitational force on an object, it's not always going to exactly equal your weight because of these three reasons. And in a minute, I'm going to do an example that'll solidify this. But so some of it is just that the mass of the Earth is not uniformly distributed. That'll make more sense here in a minute when we do the shell theorem. The fact that the Earth isn't perfectly round, right? Because it spins, that throws it partly out of roundness, plus mountains and stuff, make it not a perfect sphere. And the fact that it rotates. Okay? So, I think this next slide is the one where I have an example. Yes. Okay, cool. All right, so let's take a second and actually do some calculations and kind of see if we can use some of this and figure something out. Okay? So, let's calculate the difference in gravitational force and your weight due to the rotation at the equator. Okay? So, let's do this. Suppose you're standing at the North Pole for a minute. Okay? So, at the North Pole, here are some things. Let's make up some numbers here. Sort of page. Why don't just leave it like that? I actually like that better. Let's get in the habit of doing that. All right, so at the North Pole. Let's suppose, just for simplicity's sake, let's let your mass be 100 kilograms. Just a nice round number. Okay? The mass of the Earth is, I think the book uses 5.97 times 10 to the 24th kilograms. I've always used 5.98. But... Okay. And then the Earth has a radius of about 6.38 times 10 to the 6th meters. Okay. So, we could certainly calculate your weight at the North Pole, right? So we would do this. We'd go, oh, well, force of gravity is equal to the universal gravitation constant G times M all over R, right? And so you get 6.67 times 10 to the negative 11 times your mass, which we decided was 100, times the mass of the Earth, which is 5.97. Bear with me, this is going somewhere, I promise. All divided by the distance squared, so 6.38 times 10 to the 6 meters. Don't forget to square it. If you had to guess, what should that give us approximately? What do you got, Nate? 980, right? It's the force of gravity. It ought to be mg. Right? Okay, let's check. All right, so here we go. 6.67 times 10 to the negative 11th times 100 times 5.97 times 10 to the 24th divided by 6.38. Oh, I forgot to square it. Oh, I can still do that. Times 10 to the 6th. Don't forget to square it. And you get 978.27. We're pretty close to 90. I'm surprised the book uses 5.97. I think your book is the only one I've ever seen use that instead of 5.98. But whatever. I think that would have brought us closer to 980. All right, so are we good with that? All right, so what that means is this. If you are at the North Pole standing on a scale, keep this one. Google page, pin page. Okay, so what that means is if you're at the North Pole, you're standing on a scale, here's you, hello. That means gravity is going to be pulling you down with a force of, what did we just say, 978.23? 2 what? 27? Okay, thank you. 27 newtons, right? And what's the scale going to read? What's your net force if you're just standing there? 0, right? So, since your net force is 0, that means that the normal force, i.e. the reading on the scale, is going to be this same number, 978.27 newtons. Okay? So when the book talks about your weight, weirdly, this is what they're talking about. They're talking about what the scale is going to read. Good? Now, what happens if you're not at the North Pole? What if you're at the equator? Is your net force still going to be 0? No, why not? Because you're rotating, therefore there has to be a centripetal force, right? What provides the centripetal force? Why didn't you go spinning off of the Earth? Gravity, right? But the idea then is some of this force of gravity is sort of used up to prevent you from spinning off of the Earth, right? In other words, at the equator, the force of gravity has to be bigger than the reading on the scale to give you a net force to provide this centripetal acceleration. Follow? Questions? If you stand on a scale at the equator, it will read less than what it reads at the North Pole, and we're about to figure out how much. Christian? No, because we'll find out. It's pretty insignificant, but it is a difference nonetheless. All right, so is everybody good? All right. Okay, so. I don't know. I'd have to do the math. The Jupiter's got a bigger mass, but it's also got a bigger radius. So I'm not sure which would be a bigger factor. I'd have to sit down and crunch the numbers. So, what'd you say? I'm sorry? I honestly don't know. My astronomy is sketchy. This is where I run into trouble because physics is my minor, you guys. So, all right. All right. So here we go. We're at the equator. Well, then you're moving in a circle, right? So velocity is 2 pi r over t, right? So 2 times pi times, and I'm assuming, again, that even this is an oversimplification, I'm assuming that the radius of the Earth is the same at the equator as it is at the poles, which actually isn't true. It's a little bit wider at the equator than it is at the poles because of the Earth's rotation. Okay?
Wait, so like, the Earth is a big egg?
A little bit, yes. More like an ellipsoid, I think is the technical term for it. But yes. It's, the difference is insignificant. The eccentricity, you guys know eccentricity? A circle is 0, right? So the Earth's eccentricity is like 0.000, something. I don't know what it is. But All right, so that's our circumference, and we're going to do that in, what's the period? 24 hours, right? So let's see, 24 hours times, let's see, 1 hour, 3,600 seconds, right? So that means your velocity due to the Earth's rotation at the equator is, very good question, that is tangential velocity, yes. So let's see what we got. 2 times pi times 6.38 times 10 to the 6th divided by 24 divided by 3,600. 464 meters a second. If you're keeping score, that's 1,040 miles an hour. Just because of the Earth's rotation. Which is wild, right? That's really fast. Why don't you notice it? What's wrong? You good?
Yep.
Okay, so why don't we notice it, you guys? Why don't we notice the Earth spinning so fast? Yeah, well, everything's spinning with you, first of all, right? Okay, gravity holds you in place pretty solid, right? So when you drop a ball, that ball is moving horizontally at the same rate as you. So yeah, everything's kind of all sort of relative. All right, so now we can find our centripetal force. What's the equation? mv squared over r. So we're going to have our mass, 100 kilograms, times the velocity, 464 meters a second. Don't forget to square it. Divided by our radius, which is 6.38 times 10 to the 6th meters a second. So what's that give us? What did I write? Oh, that's weird.
Pretty fast radius.
That's good. All right. Okay, so let's see. So we're going to take our velocity, square it, multiply it by 100, divide it by our fast radius, and it gives us 0.337 newtons. So I'm going to round it up to 0.34 newtons. All right. So why is this so small? You're going really freaking fast. So why is the centripetal force so small? Yeah, because look, the circle you're traveling in is a gigundous circle. So the amount that your velocity changes each second is very, 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 very small, right? Like, right? So like right now I'm going this way. A second later I'm going this way, right? So the velocity changes just by, you know, a fraction of a degree, right? Good? Okay. So, yes, angular velocity is tiny is another way to think about it. Okay. So, but what that means is, at the equator, that's got to be your net force, right? Because you do have an acceleration. You have a centripetal acceleration. Good question. Is it down or up? Down, right? Because it's got to be towards the center of the circle, which is down, right? I almost fell over for no reason. Okay, so here we go. So here's you again, right? So gravity's pulling you down with a force of 978 point, what was it, 27 newtons. But our net force, I guess now we should probably keep track of our signs. Let's make this negative. So our net force is negative 0.34 newtons. Therefore, my normal force needs to be 0.34 less than that. Make sense? All right. So technically speaking, your weight at the equator is a little bit less, but you can see it's such a small amount that you don't need to worry about it. All right. But it is nonetheless smaller. So I guess I can do the math here. Let's see. So minus 978.27 minus 0.34. So you get 977.93.
You have to guess, is that why that NASA Institute's got the place down in Florida?
No. There's a reason why they build stuff down south, though. Anybody? And we'll talk later on about why. But
Potholes?
sort of. So you asked if that's why NASA puts, like why? What am I trying to say? Why they launched the space shuttle from Florida? Florida's close to the equator, right? And then the other one's in Texas, which is also fairly south, right? Okay. So I guess technically, yeah, there's a little bit less gravity. Is that right? I'm uncomfortable with that. There's a bigger reason, though, and Philip was really... Yeah, look. So when you're trying to put an object into orbit, it requires a certain velocity. We'll talk about that later in this chapter. Okay? Where do you already have more velocity? At the equator or at the North Pole? At the equator. So the idea is the Earth spins... Let's see, the sun rises in the east, so the Earth spins this way, right? So which way do you think they launched the space shuttle? That way, because it's already moving that way at whatever it was, 463 meters a second, or whatever it was we figured out a minute ago. Cool? All right. So, questions about this, you guys? Yeah. That's exactly correct. That's exactly correct. Because at the equator, the idea is you're not speeding up or slowing down at all, right? All of your acceleration is due to your changing direction, so it's all centripetal acceleration. Very good question. All right, are we good, you guys? Okay.
Meter would have hit you if you traveled at 1,000 miles per hour, but it came straight down 9 degrees.
Oh, I got you. Yes. Well, more you would be moving into it,
Yeah.
right?
But, very.
Yes, from your perspective. Okay, so let me get out of this dual page view. This next page is important. All right, dual page off. In big and screen. In big and screen. I feel like I'm constantly fighting with different views on this stupid thing. Okay, so check it out, you guys. All right, so shell theorem. This is big. All right. If you go further into physics and take E&M eventually, this shell theorem has some really, really important implications when you talk about E&M stuff. All right. So important idea if you plan on going into this more, or doing any E&M. All right. So here's what the shell theorem says: a uniform spherical shell of matter attracts a particle outside the shell as if the shell's mass were concentrated at its center. All right. So in English, what that means is, if the Earth, instead of being a more or less solid, more or less uniform sphere with a mass of 5.97 times 10 to the 24th kilograms, if it was a hollow shell of super, super dense something but still had the same mass, then we could treat it as though it was, a ball concentrated at the center with that same mass. Okay? So, long story short, like we were discussing before with Alex, you treat the force as originating at the center of mass. Kind of like a particle, exactly. You're condensing the object down to a particle. Follow? All right. Yes, at the center of mass.
I don't understand the shell part.
I'm getting there.
Okay.
I'm getting there. Okay, so the Earth isn't really a shell. All right? So technically speaking, so the idea is, if you're outside of this shell, then you go, all right, just for simplicity, I'm going to just use, what is 10 to the 24th? It's like billion, billion, billion. I don't know what it is. Whatever. So let's just for simplicity say that the mass of the Earth is 6 times 10 to the 24th kilograms, just so that I've got a number that I can use. Okay, for a minute. All right, so if you're floating outside of the Earth, you've got this planet with a mass of 6 times 10 to the 24th kilograms beneath you, right? So to calculate the force of gravity, you can, man, I'm having a tough time spitting this out for some reason. Instead of thinking of it as this giant object with a giant radius, you can treat it as a particle concentrated at where the center of mass is. Okay? So here's the deal, though. So the Earth isn't technically uniform, right? And it's not a shell either, right? It's a, weird thing. The center is very dense, right? The core of the planet, I think, is the densest part. Is that right? Yeah, and then it gets less dense as you go out, right? Because gravity squishes stuff, and so it's more dense, right? But so anyway, if you want to calculate your force of gravity, technically what you're doing is you're adding up all of these shells of different masses. But notice, they all have the same center of gravity, right? And it's an integral, exactly. Follow? All right, but it ends up being a very simple integral because then you just take all of the Earth's mass and condense it down to the center of mass because it's more or less symmetric. Follow? Okay, so That's sort of the less surprising part of the shell theorem. The more interesting and surprising part of the shell theorem is this. All right, well, so first of all, let's make sure we're good on the first part. So a uniform spherical shell of matter attracts particles that is outside of the shell as if the shell's mass was concentrated at its center. So if you've got a solid sphere, you can treat it as a collection of nested shells, which is what I was just trying to say there. So an object outside of a solid sphere is treated the same as one outside of a uniform shell. Follow? Sorry, I'm just reading to you. I hate when people do this to me, but I apologize. All right, so is everybody okay with that? All right, now, if you've got a shell with a particle inside the shell, it turns out that the net force, no matter where you're at, is 0. This is huge. This is like a really, really, really big result. All right, so if instead of being outside of the Earth, suppose the Earth was this mass, but again, it was a hollow shell. So it's just this super dense metal of some sort, and you climb down and you live inside it. So if you're at the very center, it makes sense that the net force there would be 0. Why? Because everything is pulling on you equally from different directions, right? Okay? But it turns out it doesn't matter where you are. If you're anywhere in the shell, the net force is still 0. Because what happens is if you're up here, and this is a little bit sloppy, but basically you can kind of think of it this way. You've got a little bit of mass above you, but it's very close. And you've got a lot of mass below you, but it's very far. And the net effect is the force pulling you down here cancels out the force pulling you up here, and the net force is 0.
What about that force?
Say that again.
What about the mass that's like really close to you, right below you?
Where?
Like right below you. Not like far stuff like that, but like what about that middle?
Wait, come, I don't know what you mean. Come up and show me where you mean.
So like this mass.
Oh wow, the belt's about right.
Yeah, like this mass is like here, but this distance is like the same.
It's hollow.
Oh, okay.
It's hollow.
Okay, I didn't get that.
Gotcha. Yeah, does that make sense, you guys, that it's hollow?
Yeah.
Okay, Alex, did you get your question answered?
I forgot the question.
Okay, so the important thing here, you guys, is anytime you have an object inside a hollow shell, the net gravitational force anywhere inside the shell is 0. Follow? All right, cool. We'll pick up here on Friday. I'm around after school today. I'm around before school in the morning. Have a good day. Yeah.
So does the Earth have a shell that's like
No, the Earth doesn't. The Earth is solid all the way through. But just hypothetically.
So what would happen if you dropped an object?
We're going to talk about that tomorrow, and you got to know this to get there. So we'll get there.
That's a lie.
It is a lot.